Hi everyone, welcome to my Z80 computer series. In this series of videos I'm going to attempt to build my own computer almost from scratch using the Z80 microprocessor from the late 70s / early 80s. So it's going to be a retro 8-bit computer similar to those from that era. So right off the bat, let's address the obvious question, which is why? Why go to so much effort to build such a low-spec machine? There are other options. We could use a more modern processor, or we could use a ready-built computer board, such as the Raspberry Pi. And let's face it, in the end, what will we have? A fairly useless low-spec machine. Well, the main reason is nostalgia. The first computer I owned was the Sinclair ZX Spectrum, which had a Z80 at its core. This is really the machine that got me into computing. I learnt to program in BASIC, but also the Z80 assembly language, so I got to know this processor quite well, and I really enjoyed working with it. Choosing such a simple 8-bit processor should make things easier. I have to consider my own abilities. I've never done this before, so I need to be able to walk before I can run. So I want to start simple. I'm already familiar with the Z80 and it's very easy to get a basic system up and running. So let's define what I mean when I say building my own computer. Sometimes when people say they've built their own computer, what they really mean is they have assembled a computer from off-the-shelf parts. You can take a motherboard, add some memory and a CPU, attach a hard drive and install it into a ready-made case, and yes, you've built a computer. And there's nothing wrong with that. It's both fun and challenging, and I've done it myself several times. But what I'm talking about here is actually designing a computer from the ground up. Okay, so I'm not designing the CPU, and yes, I will use other off-the-shelf integrated circuits or chips, as well as a few other parts, but I will be designing the whole system around the CPU. I will be designing the main circuitry and the layout of the circuit board. So this will involve drawing schematics and designing the layout and all the routing of the tracks on the PCB. Then I'll be soldering all the electronic components onto the board myself. Ideally, I want to have an integrated keyboard just like those 1980s computers from my childhood. So I'll have to think about key layouts and how to control the keyboard from the Z80 and not just use an external off-the-shelf keyboard with its own controller. I'll have to think about generating my own video signals for the graphics, but I will use an off-the-shelf monitor. I'm not going to build my own monitor. I'll also have to design any software running inside the ROMs and also design and 3D print a case. I will be taking ideas from others and integrating them into my design, but I'm not just going to copy the design from somebody else. So this really will be my own design, and it should be hugely challenging and hopefully lots of fun. I think when you build something yourself, it's your own design right from beginning to end. I think that should bring a whole lot of satisfaction at the end. A sense of achievement, if you like. So let's outline a few features I want this computer to have. So a Z80 CPU at the core. I'm thinking either 3.5 MHz or 7 MHz approximate speeds. I don't know exactly what I'm going to do yet. 256K of RAM, 64K of ROM, an integrated keyboard, maybe 40 keys, probably would be bare minimum. Color video output, exact specs to be determined later. Sound, question mark, maybe. 9-volt DC power input. I'm not going to design my own power supply. I'm just going to use a 9-volt power supply and feed this with power. Real-time clock, because it's easy, so we might as well do it. I've put here an internal SD card to act as a hard drive. Now that might be a compact flash card if it's not an SD card, but something with some storage on it. Both one inside the machine to act as a hard drive and an external one to act as removable storage, so we could swap the programs out by changing the card that's in the external drive. I'll start by trying to get the CPU running with some RAM and ROM, and then we'll work up from there. So let's start by taking a quick look at the Z80 page over on Wikipedia. So here's the page on Wikipedia. Now I'm not going to read all of this through. I'm not going to give you the full history of the chip. It's interesting reading. You can check that out yourself. Just basically says here the Z80 is an 8-bit microprocessor introduced by Zilog as the startup company's first product. And I've got a really old picture here of one that was manufactured as early as June 1976. This really is an old design. Yeah, you can read up on the history. It is quite interesting. I'd recommend you do that. What's quite nice here is there's a picture of the chip and a nice diagram of the pinout. It's a DIP 40 package. These are not DIP 40s. This is the DIP 40 package. You can see it's 2 inches long, ½ an inch wide. Back in its day, this was actually quite a large chip. They wouldn't normally manufacture chips as large as this. So it was to some degree a bit of a risk to switch to a larger package. And you can see here there's the pin out. Now this is like an abstraction, just showing the pins in a bit of a neater format because they're not actually arranged like this on the chip. You can see here we've got pins 1, 2 and 3. They would actually be, this would be pin 1 here, so it would be 1, 2 and 3 going down there, and then back up this side, and pin 40 would be here. Whereas on this abstraction you've got pins 1 and 40 next to each other, just to make it a little easier to understand. And you can hopefully see straight away this is going to be relatively simple to connect up. Although it's described as an 8-bit processor, it actually has a 16-bit address bus. We've got here A0 to A15, that's the 16-bit address bus. So with that we can directly access up to 64 kilobytes of memory. The processor doesn't care if that's RAM or ROM, it's just memory. As far as the processor is concerned, it treats RAM and ROM the same. And then we've got the 8-bit data bus. We've got VCC and ground here for a power supply. We've got a clock signal to keep things running at a steady pace. And then we get 13 control lines, which is quite a lot, to control the kind of rest of the system. And 4 I'm going to draw your attention to are these 4 here. This is memory request, IO request, read and write. I've got that around the wrong way, haven't I? It's write and read. And what's interesting about the Z80, it actually has its own I/O address space. So whereas we've got this 16-bit address bus for the memory, we actually get 8 bits for the I/O. It just uses the bottom 8 bits, A0 to A7. And you can actually, the processor will tell you if it wants to access I/O, like peripherals, or memory. If it wants to access memory, it will pull this line low. And if it wants to access I/O, it will pull this line low. So you could just look at these 2 lines, connect them up to your hardware, and know that your I/O needs to be sort of active when this line's low, and your memory needs to be active when that line's low. And then the system will also tell you whether it wants to write or read to that memory or I/O address location, the address that's appearing on the address bus. So you can basically use these 4 lines here to control the memory and the I/O, which will be connected at any point in time, so that the correct device is connected to the address bus and the data bus at the right time for the processor to access it. And that is kind of super easy, as we'll hopefully see probably in the next video when we get into that. There are a few other control lines here. There's a halt line, a wait line, some interrupts, non-maskable interrupts, a reset line, bus request and bus acknowledge. It's starting to get a little bit more advanced with interrupts and bus requests. So we won't be covering those for quite a few videos yet, but most of this is going to be pretty simple. Let's move over to a schematic of what I've built up on the breadboard here. I've broken it down into different sections of the circuit. I'll show you the schematic of a particular section, and I'll show you where that is on the breadboard. Let's start here with the power supply. So it's an LM7805 linear voltage regulator, and that is here on the circuit board. I'm not going to build this circuit up piece by piece. I'm going to just show you the schematic, and then I'm going to, if you want to follow along, you should be able to follow the schematic. You can see here on the schematic we've got 9 volts coming in, and it's, you may have noticed I'm powering this from a 9-volt battery. I wasn't sure if that would work, if that would produce enough current, but you can see it's running, it's working perfectly fine. So for a little mock-up system like this, the 9-volt battery is fine. The red wire there is the 9 volts going in. It goes in that little pink wire down there into pin 1 on the voltage regulator. Pin 2 on the voltage regulator, this little black line down the bottom here, that's ground. And then pin 3, the red line coming out of this side, feeding this whole red rail across the bottom. And it's also both the red and the black are linked to the top rails as well. That's the 5 volts output from the voltage regulator, that's here. Now I've just got 2 capacitors on here, one on the input and one on the output, and although my diagram says 330 nanofarads, I didn't actually have a 330 nanofarad capacitor, so these are the 2 capacitors here, and they're both 100 nanofarads, and it works perfectly fine. Now, I looked at the data sheet of the 7805, and I did lots of reading, and I noticed that people were doing all sorts of different things. And I think the point is to calculate the size of the capacitors. You really need to look at your overall system. So there isn't like a one-size-fits-all. You need to be looking at your overall system. I'm not going to go into that. I mean, you can see it's working here, so if you follow along with what I've done, you should be able to get it working. So moving along, we've got the reset circuit on the schematic. Now you've got 5 volts at the top there. Now that's actually pulling up the reset line through this 1K resistor. So we've got a switch here on the ground. So when the switch is open, when the switch is not pressed, reset line will be at 5 volts. And when you close the switch, current will actually flow down through the 5 volt line, through the closed switch down to ground. That's conventional current, I should say. So we'll point out that is not electron flow, that's conventional current. I will always talk about conventional current. I'm not going to keep repeating that. So current will be flowing, therefore there will be a voltage drop across the resistor, and we'll actually have 0 volts here. It's pretty obvious we'll have 0 volts because this will be directly connected to ground. So that'll be 0 volts when it's closed. Pull-up resistor is important. We can't just connect the reset line straight to 5 volts because when we close the switch, we would have no resistor. We'd have a dead short between 5 volts and ground. We would draw too much current, we'd burn something out. So the pull-up resistor is important. Now again, values of pull-up resistors, that's a whole topic on its own. Pull-up resistors typically range from about 1K to 10K. I just used 1K resistors here because I was looking at other people's example circuits. It was working for them, so I just followed along. And we can see that here on the breadboard. This, I believe, this switch is the reset switch. There's the 1K pull-up resistor to the 5 volt line going to one side of the switch, and then the other side of the switch just goes down to ground through this black line. And then there should be it's the orange wire across the top here. Is actually the reset line, which is this reset flag on our schematic. It's going into the reset line of the CPU. Let's keep moving along. Now, this is the clock generation circuit. It's a little bit more complicated. I'm going to do my best to explain it, but you might have to bear with me a bit. My knowledge is weak on this stuff. I'm actually using an integrated circuit here called a 74HC14N. Again, I selected that because I saw other people were using it. It was working for them. So I got one of those. You can see that chip here, and it works for me. So I'm happy with that, at least for this point. In the future, we might do something different for the clock. But this is just a demonstration board. So these are what I call slow clocks. The diagram here is split into, it says here manual and auto clock. Now there's an automatic clock generation circuit down the bottom here, and then there's a manual clock generation circuit at the top. We'll explain the manual one first because it's very similar to the reset circuit. So we've got the plus 5 volts, and this time we've got a 10k pull-up resistor. And it is actually slightly different here because we've got a capacitor down here, but there's the 10k pull-up resistor, and then there's the switch going straight down to ground. So when the switch is not pressed, we would actually have 5 volts at this point here, and what would actually happen is the capacitor would charge up. So it wouldn't appear at 5 volts immediately. It'd be like a slow curve ramping up to 5 volts. Once that voltage reaches a minimum threshold for the input of this chip, then the output will switch on suddenly. It'll be like a digital signal on this side. So this side of the circuit is kind of analog, ramping up slowly, and this side is digital, switching on immediately. And we do that so we get a nice clean signal. It's called debouncing. We're debouncing the switch because when you press the switch, what actually happens is the switch sort of bounces and it opens and closes several times really fast. And you normally wouldn't notice that, but it can mess up circuits like this clock circuit. And this is actually an inverter. So when we've got 5 volts here, we're actually going to have 0 volts here. So it's going to take the clock line low. And this whole circuit, the manual clock circuit, will only be in effect if we've got this dip switch closed, the top one closed there, going to the clock line. So the way this works is we close either one or the other of these switches to get either the manual clock or the auto clock. Now if we look at the auto clock, it's doing a similar thing, but it's doing it automatically without us having to keep repeatedly pressing a button. Now again, I'll do my best. There's two inverters here in series, but I think we can just look at the first one to start with. Now this circuit confuses me because there's no kind of feed coming into this, but you have to remember that these chips do have internal power supplies, so there is some voltage coming in somewhere. It's just not shown on this diagram. And that is actually an important point. I haven't shown the power connections for this chip, and these inverters here, they're labelled 2.3, 2.1 and 2.2. They're just different inverters on that same chip here. So all of these devices are actually one integrated circuit, and that integrated circuit has its own power supply. There's a 5 volt power supply coming in here and a ground here feeding this chip, powering this chip. Now that is important, and it's not shown on the schematic. So I actually, when I turned this on, I couldn't figure out why it wasn't working. I put a scope on it, an oscilloscope on it, and nothing was happening. And then I had the duh moment and realised, oh, what an idiot! I haven't connected the power supply lines. I'm fully aware that they need to be connected. They weren't on the diagram, so I just forgot them. So it's an important point. Make sure you connect the 5 volts and ground to this chip. Let's go back to this auto clock circuit. Now, if this connection here is low, then the inverter would make this side high, and some current would flow through this feedback resistor here, charging up this capacitor, which would, as we said before, the capacitor will slowly charge, and it will make this input here high, which will then switch off this side. The current will stop flowing, the capacitor will discharge, the voltage will drop down low, and when it drops to a certain point, it will switch again. And it will just keep switching backwards and forwards between high and low, and the frequency, which allegedly is about 2 Hertz, but I think I measured it a little bit different than that. The frequency is controlled by the RC ratio here, the resistor and capacitor network. So if you vary these values, you can vary the clock speed. You could use a variable resistor here, I guess, and have a variable speed clock that you could adjust on the fly. I believe the last inverter here is just to clean up the signal. I'm not 100% certain why the second inverter is there. I believe it's just to clean things up before we finally take the output to the switch selection circuit here. So hopefully that explains the clock. Let's have a look at that on the breadboard. So the manual clock is here, it's this button here. We've got the pull-up resistor and the capacitor down the bottom, again 100 nanofarads. What was that? That was a 10k resistor. That's the only 10k resistor. All the other resistors on here are 1k. Some are blue, some are brown, but they're all 1k, with the exception of this one here, which is 10k. So that's our manual clock switch. And you should see the yellow line here is feeding into an inverter, which is here on our diagram, pin 5, and actually comes out of pin 6, which I think is this line here, and it feeds into the first switch. And then our auto circuit is mainly on the chip, and this resistor here and this capacitor here. And that is coming out eventually out of pin 4, which I believe is this one down here. So that's pin 4, and that's feeding into the second switch. You can see the other side of the switches, they just link together via that little link. And then finally we've got the clock line coming out, going into the processor. So that's our clock circuit here. Now this is important, so we'll look at this first. Unused gates. This is important. Pull all the inputs of any unused gates down to ground. I think you can pull them down to ground, or you can pull them up to 5 volts. Doesn't make much difference as long as you've tied them to either high or low. So I've tied mine all down to ground. I think I did a previous video on clock circuits similar to this. It was a little different, and that really cleans up the signal. So that's something now I'll just do as a matter of course. Any unused inputs, pull them down to ground. So that is important. Don't miss that step. I've shown a couple of bypass capacitors on the circuit diagram, because if I built this up properly on the circuit board, I would include a 100 nanofarad capacitor on the supply of this chip, and another one on the supply of the Z80, but I haven't actually connected them up on here. Not terribly important at this stage, but if you're going to build something more permanent, I would definitely fit them. So that then really just leaves the actual Z80, and what we've got is a whole load of LEDs. You can see here the fancy flashing blinking lights where all the fun happens, connected up to this Z80 processor. So let's tackle these a few at a time. Here's our address lines, our 16 address lines. Now, I've only connected up the first 4, and I've got them connected to some blue LEDs. These are the blue LEDs here. You can see we've got some current limiting resistors, 1K resistors. Now I was a little concerned about connecting LEDs that might draw quite a lot of current directly to the chip. It didn't seem like a very good idea, although I've seen people doing this lots of different people have done this, and it doesn't seem to cause a problem. So I did a little bit of maths, and I just thought, without going, I never like going into the maths. So to keep things pretty simple, I figured this is a 5 volt system, so the maximum voltage we're going to have on these pins is 5 volts. Now if we had no LED at all, if we just had the 1K resistor, 5 volts across 1K would mean a maximum current of 5 milliamps. So the absolute maximum we're going to be drawing on any of these pins is 5 milliamps, which is not that much, although it's still, it's a little bit. But once we've got the LED in there as well, which is going to drop at least 1 volt, probably more like 1.5 volts, or even as much as 2 volts, depending on the color of the LED. We're going to be nowhere near that 5 milliamps. We're going to be definitely under 4 milliamps. So I think this is safe. Now I actually tried to look for a data sheet for the Z80, but to find out how much current you can draw on the pins, and I could not find anything anywhere. So if anyone can point me to some reference material to show me how much current you can pull on the pins, that might be interesting as the design grows and gets bigger. Although we definitely we don't really want to be doing this in a permanent design. So they're the address lines, just the first 4 address lines. I didn't think it was worth connecting all the others up. Then on the other side of the chip here, I've got LEDs connected to the M1, the memory request, the IO request, the read, the write, and the halt. So 6 lights. Green is the M1 line. That is here. You can see that is blinking. Now we've got memory request and IO request are pins 19 and 20. I believe they're the last 2 pins down on the bottom corner of the chip here, and they're these 2 here. I believe it's the read light which is flashing, which would be, sorry, it's the memory light which is flashing, which would be pin 19, and this is the IO request which is not being used, so hence it's not flashing. Then we've got read and write, I believe are these 2 here, and again it's the read one is the one that's being used, and the write is not doing anything. The halt line is here in red, currently not being used. Now, what's important with these LEDs is the way you connect them. Now, the address lines are active high, meaning when that address line is active, it's a high voltage, like +5 volts. So we need to connect the LED, because LEDs are polarized, and it's important which way round you put them in your circuit. You want the anode connected to the 5 volts and the cathode going down to ground. So these have got the current limiting resistors here. The position of the current limiting resistor doesn't matter in respect to the LED, it just has to be in the circuit. But I've got my 5 volts going through the current limiting resistor, and then these are connected to ground on here. It might be a little bit difficult to see because I'm not really showing you a good picture of the breadboard, but they're connected to ground. It does show that here on the diagram. See the anodes here, the +5 volts on the active high lines, and then the cathode going down to ground. Whereas on the other side, it's the opposite way around. They're actually connected. The anode is connected to the +5 volt rail, and these lines are all active low. That's what this slash means. You get different notations for active low. Sometimes you'll get an exclamation mark. Sometimes you get a bar drawn across the lettering, and sometimes you get a /, but they all mean active low, which means when the M1 line is active, it will be low, it will be 0 volts. Now I wanted the light to come on when it was active, so I've connected the anode to the 5 volts, and it gets switched on the low side. The current flows from the 5 volts into the chip, whereas on the address lines it's flowing out of the chip. So again, that's important, because originally I didn't do that, and the lights were kind of working backwards and it was confusing me, so that's important. There are a few other pull-up resistors here. We've got one on the wait line, one on the interrupt line, and one on the non-maskable interrupt line, and another one on the bus request. I think these are all the input lines to the chip, the input control lines, so we need to pull them high. We don't want that feature. We don't want the wait to be activated, and we don't want interrupts to be activated. So they're active low, so to disable them we pull them high with a pull-up resistor connected to +5 volts. We'll come back to we've already talked about the reset line and the clock line. They're being fed from the circuits that we spoke about. There's the +5 volt and ground. +5 volt is here, the red wire, ground is there, the black wire, but look at the schematics, look at the pin outs, you can figure out all of that yourself. Now here's the data lines. Now that's the green connections on here. This is the trickiest thing to build. It's the main reason why I didn't want to dismantle all this and rebuild it sort of step by step so you could follow it through, because it was just tricky to get everything to work. So these are the data lines D0 to D7, and they don't neatly go across the chip. They're dotted about all over the place, so you need to be careful that your D0 wants to be going to this switch, I believe, because we're going to use these switches. They're here on the diagram here, 8 dip switches, and we're going to use those to essentially give the chip an instruction to execute. This design, the chip can only read the one instruction. This is essentially our memory. and we've only got one memory address that it can actually read from, or the fact that they're permanently connected to the data line, whatever memory address the chip is reading is always going to get whatever is set on these switches. So you'll always get the same instruction over and over again, which is why it's kind of neatly blinking. But when we work in binary, we work from right to left. So this is our least significant bit here, and that wants to be the D0 line. This will be D1, D2, D3, D4, D5, D6, and D7 being the most significant bit. And then they're all pulled down through pulled down resistors. They're here on the circuit diagram, and they're these row of resistors here on the circuit board. So when the switch is open, the pins will have 0 volts because they're pulled down with the pull down resistors, and when the switch is closed, the other side of the switches is all connected to the positive rail. So when the switch is closed, we'll get the plus 5 volts. I believe we could have done it the other way around. We could have pull up resistors, but I've just done it this way. So that is the full schematic, I think. So I think it's time to explain what is going on here. Now, I did already allude to it a bit. When you first turn on the chip, providing it's had a clean reset, which it doesn't always, so you may have to hold down the reset line, and if we do that, you can see it kind of goes dead. If you hold it down for a certain number of clock cycles, so I'm on the automatic clock, so I could just hold the reset line down. If I was on the manual clock, I'd have to hold reset down and manually clock it a few times. When it powers up, it goes to memory address location 0. If we just do that again and watch the blue lights, we should see it starts at memory address 0, which will be a little bit difficult to see because it will be all the lights will be off, and then it will go to memory address 1, and then it will go to 2, and then 3, and then 4, and then 5, and then 6, and then 7, then 8, 9, 10, 11, 12, 13, 14, and finally 15. It's in binary, and it appears to have started again, but it's actually continuing to count up 17, 18, 19. It's just we haven't got the extra lights here. And what is happening is it's doing what we call a fetch, decode, execute cycle. So it will fetch from memory. So the memory line will go low and the read line will go low, and it will fetch from memory and it will get whatever's on these pins. Now I've deliberately connected them, or I've switched them all to the off position. They're all down. Now if we look at the manual tells us all the instructions, but on page 180, and I'll leave a link to the description in the manual, is what we call the NOP code. Now that stands for no operation. Basically means do nothing, but even doing nothing actually takes time, and once we look into this a little bit more, you realise there's actually quite a bit going on even when it's allegedly doing nothing. So you can see that all the bits need to be set to 0 to give us that that NOP instruction. So it'll execute that NOP instruction, and then once it's finished executing that NOP instruction, it will just move to the next memory address. It will read again, and it will get the same NOP instruction again, and it will just repeat and keep executing the NOPs. Now you can see in the manual the NOP description says that we have 1 M cycle and 4 T states. Now these are machine cycles and time states, and then it gives you an example here that if you've got a 4 megahertz clock, the estimated time would be 1 second. Don't know what the 1 would be. So I think we have to have a quick look at what is actually going on in that NOP cycle. It's quite interesting once you start looking at the timing of what's going on these pins, because if you look here, you can see the M1 line is coming on, and then slightly afterwards the read light comes on, and there's some slightly different sequence going on here with the memory request line. Okay, so here is the basic CPU timing example from the manual on page 8, and you can see the first part of it. There's the machine cycle called M1. There is actually an M2 and an M3, but we only get the M1 line on the board available to us, which is our green LED. Now you can see during that M1 cycle there are 4 T cycles. It's just an example. I'm not sure if it's always the same, but this example here has got 4 T cycles. So you can see the clock line will go high and low 4 times to one machine cycle, the M1 cycle. I believe it's different for M2 and M3, and I'm not sure if it's always the same. The next thing I want to show you is the actual the opcode fetch, which is the main thing that's going on here. Is it's fetching our NOP instruction. At the top we've got the clock line, and you can see that the 4 T cycles, it's going high and then low. Now at the end of each T cycle is what we would see. If we switch this over to the manual clock, we'll just turn that off. Make sure that doesn't fall out. Okay, I'm going to give it a reset, because you never know what happens when you switch the clock over. You could get weird glitches. So I will press the reset and hold it down, and then I think we have to give it at least 4 clock cycles. Give it a few more just to make sure. And now that is reset. Now if I press the manual clock, I think that you have to do a few, I'm not sure how many, on the initial startup after a reset. You have to do a couple, and then it will go into this this M1 cycle. So we'll give it a few pushes. That's 1, that's 2, and then on the 3rd press you can see the M1 light came on. So we're basically at the end of that first T1 cycle, and we should see our memory, whereas the M1 line is here. You can see at the end of that T1 it's low, and active low means our light comes on. But we've got some other lights on as well. We've got the read and the memory request lines, and there's memory request. You can see indeed it is low at the end of T1, and where is read? Here is read. That is also low at the end of T1. But you will notice that the time that happens is actually just slightly different times. The M1 line will go low first, then memory request will go low, and then read will go low. So that's why they're not all the lights are not blinking at the same time, but at the end of the T1 cycle they are, all 3 of these lights are on. Now if we press it again, nothing appeared to happen. Let's have a look at our timing diagram again. We should now be at the end of the T2 cycle, and we've got memory request is indeed still low, read is still low, and M1 is still low. So that's all good. We press it one more time. Now the M1 light has gone off, and so this is the read light. No, this is the memory request light. The one that's on is memory request. So the read light has gone off and the M1 has gone off. Look at the manual. We're at the end of the T3 cycle. So memory request is, it actually briefly went high, which means our light would have gone off, and but it then comes on again. So it's on at the end of the T3 cycle, but the read light went off and stayed off. It's high means it's off, it's active low, and the same with the M1. The M1 and the read kind of go off pretty much at the same time, and they stay off. The memory request is turned off but then turned back on again, and that is what we are seeing here. And if we give it one more press, that light finally goes out, all lights are off. At the end of the T4 cycle, we've got memory request is high, read is high, and M1 is high, so all lights are off. So this is behaving exactly as per the timing diagram. So gives me a bit of reassurance that what I'm seeing here is actually all working, and it also gives us a reasonable understanding of what's going on as part of that fetch cycle of reading a memory address. Now if we press the button again, we'll go into, the process will repeat and we'll end up in the M1 cycle again at the beginning, and there we go. We've now got the address line is incremented, we've got the M1 light on, and as we step through it, 4, and again we're into the third instruction. So that's all working, that's very nice, but it would be nice if we could see this halt line. Now there is a halt instruction in the manual, I've just got to find it. Where is the halt instruction? It's on page 181. It's actually the very next instruction after the NOP. There it is, halt, page 181. So this is 0111011. So if I just change these, so we need 0. How can I do this? Bear with me. 111 and 0110. And if we're on manual clock, so if I keep stepping through, we should eventually see the halt light come on. So it executed our halt instruction and pulled the halt line low. Now I think just one more would be interesting to see the IO request line, because we saw the memory request but we didn't see the IO request line. So if we find an out instruction, out n, A, that should do, page 306. You can find that. There we go, 306, out n, A. So if we set the dip switches to 110, 1, 0011, that should be, if I've got that right, that should be out n, A, and we can just continue to manually step through. And this is a memory read because it needs to actually read the instruction from memory. I think what's happening here is we're actually in a halt condition, so I'll need to give it a reset. So we're fully reset and it should start up and read our output instruction. There's the M1. Again, I believe that's a memory read, so it should read the instruction. And then eventually we do get to the IO request line has come on. So I think we've demonstrated every single LED that we've got on here now, and we've proved that this little demo circuit does work. It's given us a reasonable understanding of how the fetch cycle works, at least. And we've got manual clock, we've got automatic clock, we've got a little power supply. We've got an entire system here, but it's not that useful. What we need, the next step, would be to add some memory that we can store a program into, and for that we're going to attach a ROM chip. So we'll look at that in part 2. So I hope you're enjoying this so far. Please leave me some comments. I'd love to have some feedback on what sort of things you want to see me talking about. And I'll hope that some of you at least maybe follow along with me and have some fun with your own Z80 computer. So thanks for watching, and I'll see you in the next one.